One of the hottest trends in the field of designs, in particular architectural designs, is the adoption of AI and machine learning techniques to complement and enrich the architect's workflow. As one of the most fundamental elements of architecture, floor and building plans have drawn recent interest from the computer graphics and vision community, including raster to vector floor plan transformation, floor plan reconstruction from 3D scans, and floor plan and layout generation. In this work, our goal is also to generate floor plans from given building boundaries. However, one of our key observations is that user preferences for a target floor plan often go beyond just a building boundary, but also include more specific information, such as room counts or connectivity, which can be best represented by a layout graph. Hence, our framework consists of two key components. One is a layout graph recommendation, which takes the building boundary and sparse user constraints as input and output the suitable layout graph. The other core component is a learning-based generation method, which converts a layout graph, along with a building boundary, into a floor plan that fulfills both the layout and boundary constraints. Note that since the layout constraints are typically sparse, these can lead to more than one suitable layout graph, and in turn, multiple floor plans can be generated by our method for the user to select and explore. For the layout graph recommendation, we adopt a retrieve and adjust process, where the layout graph is retrieved from a human-designed database based on user constraints and then adjusted to the given boundary. To build such a layout graph database, we utilize the large-scale floor plan dataset, RPLAN, introduced by Wu et al. 2019, consisting of more than 80,000 human-designed samples. For each floor plan, we extract the bounding box of each room and the connectivity between rooms, and represent all this information in a layout graph. More specifically, for each room, we encode its type, size, and location information in the corresponding node, and for each pair of connected rooms, we encode their spatial relation in the corresponding edge. Given an input building boundary, users are allowed to specify different kinds of layout constraints, such as room numbers, locations, and adjacencies. We then retrieve a set of layout graphs that satisfy the given user constraints from the database, and rank them based on the boundary similarity, since buildings with similar boundaries will be more likely to have compatible floor plan designs that can be transferred to each other. For each retrieved layout graph, we automatically transfer it to given building boundary by rotating and scaling the graph to match the front door location and bounding boxes of the building boundary, and possibly refining the node locations if they appear outside the given boundary. Users can also further edit the automatically adjusted graphs by moving nodes, deleting existing nodes or edges, and adding new nodes or edges. To generate a floor plan from a layout graph and building boundary, we designed a deep neural network that we call Graph2Plan Net. To first output a set of room bounding boxes and raster image of the floor plan, and post-process the output of the network to obtain the final vectorized floor plan. The Graph2Plan Net takes as input a layout graph and building boundary, and generates a set of initial bounding boxes for all rooms. Then, those boxes are further used to generate a raster floor plan image to provide more global constraints. After that, both the initial boxes and raster image are passed to a box refinement network that locally refines the location and size of each room box. In addition to using common regression losses defined on the boxes and images, we introduce 4 geometry losses on the initial boxes, which include a coverage loss to ensure that the building is covered by the union of all boxes, an interior loss to constrain boxes to the interior of the boundary, a mutex loss to prevent overlap among room boxes, and a match loss to constrain boxes to cover the same region as their ground truth counterpart. The final output of Graph2Plan Net is a raster floor plan image and one bounding box for each room. An issue that may occur with the output boxes is that they may not be well aligned and some boxes may overlap in certain regions. Thus, in the final vectorization step, we improve the alignment based on the spatial relationships encoded in the edges, and at the same time use the raster floor plan image to determine the room label assignment in the regions with overlap. Here are some final vectorized floor plans, obtained with our method given different boundaries and user constraints. To facilitate the floor plan generation, we designed an interface for users to add constraints and explore and edit the generated floor plans. Here's the demo. Once a building boundary is loaded, floor plan design examples with similar boundaries are retrieved from the database, and the snapshots are shown in the list box in the middle of the interface. If the users have specific constraints on the numbers of different room types, they can specify the constraints in the top filtering bars and search the floor plans that satisfy all the constraints. If the users want to further add constraints on room location or adjacency, they can add specific type of room nodes inside the boundary and add edges between the nodes, and then search. The users can select any retrieved floor plan and study them in detail in the right window. If the users like the suggested design, they can click the Transfer button to transfer and automatically adjust the layout graph to make it fit into the input building boundary. The users can further edit the graph by moving nodes around, deleting or adding edges, and even deleting or adding new nodes. Once the users are satisfied with the layout graph, they can click the Generate button to generate a corresponding floor plan. After that, the users can iterate the process by further editing the graph and refining the floor plan. Please refer to the paper for more details. Thank you.